In our previous lesson, we took a look at the idea of intersections of a line with another line in R3. And I pointed out to you that it was mostly similar to what you had already done in the past with regards to intersections of lines in R2. This is going to be mostly similar to what you did with the intersections of lines with each other, so a line and a line, when it comes to the algebra. So we're not really going to be doing anything new algebraically here. And as you can see from the note on this first page, the results are still the same. They're still organized the same way. We can have no solution, we can have one solution, or we can have infinite solutions. The algebra that gives you these three results is going to be very similar. The difference is conceptually, what are we talking about? And there are going to be a couple of new things that we add in as far as how can we get there. So when we're talking about a line and a plane, I've got the textual descriptions here, which you should capture in your notes, but it's easier to see this with some diagrams. And of course, I don't have diagrams to start, so let's go to the diagrams. So the way that we talk about these things, I've got the planes, various planes represented with this green shaded parallelogram. But you have to imagine that that's a flat plane that's kind of laid down to its side. We're trying to imagine this as a 3D space. So if I have a line running through the plane and that line is at a right angle to the plane, well, we're going to end up with a point of intersection right there where the line pierces the plane. Now in this particular case, what we have is that the line is perpendicular to the plane, and I've represented the normal to the plane with this red vector. So that's the normal to the plane. And this other would be, well, that's the line. I don't want to draw that as a vector because I've actually got arrows on both ends of that. But this line would have a direction vector. And so I guess what I can do is along this line, I could draw in the idea of a direction vector. And then what could we say if we were comparing these to each other? What could we say over here? Let's move to the second diagram. We've got a line, again, piercing the plane, which means there's going to be a point of intersection. And then we've got a normal vector. Now in this case, one thing that it might occur to us to do is to take the dot product. And in this case, when I have two vectors that are lying in the same direction, what can you tell me about the dot product? Or more specifically, what is the dot product not going to be? And the dot product is not going to be zero. It's going to be a non-zero dot product. And that's going to be the same regardless of the order that you do this in, because dot product is commutative. So that tells us if we end up in this case, the dot product is non-zero, that resulted in a point of intersection. Now what about over here? In this case, if I move that normal and kind of line it up with the exact point of intersection, that would be some angle. There'd be some angle between the normal and the direction vector. And once again, that angle would yield a result that the dot product would not be zero. Now, these are the more difficult cases to understand, or not to understand, but to visualize. In this case, we've got our plane, there's our normal vector, and the line is lying completely within the plane. So in this case, we actually have infinite solutions. So over here, we had one solution. And with this one, we also had one solution. With this one, we have infinite solutions. And is there anything that we can observe about the fact that we have infinite solutions? Once again, if I put in a direction vector d and I shift over that normal so that they line up, well, the fact that the normal is perpendicular to the plane and the fact that the line is within the plane, that means that the normal is perpendicular to the line. So the normal vector is perpendicular to the plane. That's what it means. That's the definition of a normal vector. And that tells us that the normal vector is perpendicular to the direction vector, or the line. And that tells us that the normal vector dotted with the direction vector must be equal to 0. The angle between them, this angle theta, must be equal to 90 degrees. And that's for infinite solutions. Now what about over here? Here I have my plane, and then my line is actually parallel to the plane, but it's not within the plane. So in this case, I would put my direction vector here. But if I do that, notice that I'm still going to get a right angle between the normal and the direction vector. So for no solution, I also end up with the case where the normal dotted with the direction vector is equal to 0. So by taking a look at these four fairly common or simple ways of looking at it, I've actually accounted for all the possibilities. One solution occurs whenever the dot product is non-zero. Infinite solutions and no solution both occur when the dot product is equal to 0, and that means we'd have to do more math in order to distinguish between these two cases, and we'd have to do more math in order to narrow down what the actual solution is, to find out the x, y, and z coordinates. So let's go back to that example that I was going to start with here, and I'm going to show you now that the algebra is actually very similar to what you've been doing so far. Find the intersection of the line and the plane. I give you a vector equation of a line, so we would call that the line L, and I've given you the Cartesian or scalar equation of a plane, and that is often given the Greek letter pi, which it's the letter P. It's for P for plane. I don't know why that decision was made, but it was made. So this pi has absolutely nothing to do with 3.14 in this case. In this case, pi is just being used to represent the letter P for the word plane. Now, in order to work between my vector equation and my scalar equation, the thing I'm going to make use of in this case is the fact that I already have an x, a y, and a z in my scalar or Cartesian equation. So what I'm going to do is I'm going to take my vector equation and put it into component form. So the x component from my vector equation is my initial x component, which is 4, and that's going to be negative 1 times t, so that's going to be minus t. My y component from the equation is going to be 6, and that's going to be plus 2t for the direction vector. And then z is going to be an initial value of negative 2, and that's going to be plus t. And now that I've got this in parametric form, the x, y, and z are all expressed in terms of the t parameter. Now that I've done that, I'm actually going to sub these in. So I'm going to sub in x, I'm going to sub in y, and I'm going to sub in z. Now I'm not doing this blindly. Yes, you see an opportunity here, oh, I'm going to write this and I'm going to sub it in, but I want you to think about why is that a good idea. By substituting in my parametric equations, this Cartesian equation is going to get rid of the x, get rid of the y, get rid of the z, and we're going to end up with a single expression in terms of t, which I can then solve. That's going to tell me the particular t value where this line crosses this plane. It's going to tell us the particular value of the parameter t that we can plug into this line and find the point of intersection. Of course, that depends on this actually working. So let's go ahead and make those substitutions. So I'm going to say 2, and then instead of the x coordinate, I'm going to put the parametric form 4 minus t. And then it's going to be minus, and instead of the y value, I'm going to put 6 plus 2t. And then plus 6 multiplied by the z coordinate, which is -2 plus t, plus 10, which is that d value, the constant, and that's equal to 0. So some expansions here, I get 8 minus 2t. Be careful because you've got a negative here, so that's minus 6 minus 2t. And then you've got plus 6 times -2 is minus 12. And then positive 6 times positive t is plus 6t. Plus 10 is equal to 0. And from there, it's just a little bit of cleanup because I want to bring, let's see, I'm going to end up with, well, let's do everything on one side to start. So let's start with our constants. 8 minus 6 is 2. 2 minus 12 is -10. -10 plus 10 is equal to 0. -2t minus 2t is minus 4t. Plus 6t, -4t plus 6t is plus 2t is equal to 0. And of course, that 0 doesn't need to be there, so we end up with 2t equals 0, which is the same as t is equal to 0. Now, it's easy to get to this point and actually worry, like, is this somehow invalid, t equals 0? You need to understand that t equals 0, we've constantly written that this parameter is t member of R. T is allowed to be 0. T is a valid result. It's kind of convenient in this case because what it's saying is that my position vector is pointing to the plane. So the position vector, which is this one, which is R naught, this whole thing is already pointing to a point on this plane. And the way we would show that formally is to say what we're going to do is to find our point of intersection. We're going to find our point of intersection, we set t equal to 0, or we sub t equal to 0. So we end up with r is equal to the position vector 4, 6, -2 plus 0, and I'm just going through the formality of this, times -1, 2, 1, which of course just stays 4, 6, -2. And that is a position vector, and so therefore the position vector points to the point of intersection. My point of intersection is the point 4, 6, -2. Okay. For my second exercise, what we're going to do is we have the question, the first part that we're going to deal with on this page, is there any way to predict the number of solutions? Now, we went through our possibilities here, and when it comes to predicting the number of solutions, it comes down to the dot product. So let's go ahead and take a look at the dot product between the direction vector. So we're going to want to do the dot product between the normal vector of the plane and the direction vector of the line. So can we get one or both of these? Now the first thing you need to recognize is that here is our line and here is our plane. So can we get one of these? Can we get the normal vector? Yes, we can. The normal vector, if you've got a plane in Cartesian form, the normal vector comes from the a, b, and c values. So that's going to be 2, 3, and -4. From the line, our direction vector, that's going to come from the coefficients of the parameter. So in this case, I've got a direction vector of 1, 2, 2. And now that I have that, I can evaluate the dot product, n dotted with d, and that's going to be, n is the x component is 2 times the x component is 1. So that's going to be 2 times 1 plus 3 times 2, so the y components, plus -4 times 2 as well. And so I end up with 2 plus 6 minus 8, and that gives me a value of 0. So my dot product is 0, and that the interpretation of that, so that means theta equals 90 degrees. But what does that actually mean? Theta equals 90 degrees. That means the line uh, or sorry, I shouldn't say that way. Let me go back here. I'm going to say that means that my normal vector is perpendicular to my direction vector, and that means which of these two diagrams, or sorry, which of these diagrams applies. We had the dot product equal to 0, so it must be one of these two situations. So the normal is perpendicular. The normal is perpendicular to the direction vector, and so we either have infinite solutions or no solution. So that's the first thing. Can we predict the number of solutions? We've predicted it as well as we can, so therefore it's either infinite or no solution. But we can't go any further than that without going deeper into the algebra. So that's the prediction. Then we actually try to determine the intersection. And how do we do that? We do it the same way we did in the previous question, which is we're going to make a substitution. So instead of x, I'm going to write this as 2 times 5 plus t plus 3 times 4 plus 2t minus 4 times 7 plus 2t minus 7 equals 0. Now I'm down to a single unknown, which is t. So 10 plus 2t plus 12 plus 6t minus 28 minus 8t minus 7 equals 0. 10 plus 12 is 22. Minus 28 is negative 6. Minus 7 is negative 13. 2t plus 6t is 8t. Minus 8t is 0t equals 0. And of course, 0t is just equal to 0. So now we end up with negative 13 is equal to 0, or 0 equals 13. They're the same thing, and obviously neither of these, so that is not possible. Using the same terminology that we've used in the past, that would mean that this is an inconsistent system. Therefore, there is no solution. There is no value of t that can make this true. And so what's the situation that results in this? That would be a plane with its normal vector, and the line is actually parallel, which that's a terrible job of drawing a parallel line. The line is actually parallel to the plane. But distinct, meaning it does not lie in the plane. And that's it for this lesson. As I mentioned at the beginning, this is really, from a skills point of view, this really isn't very different than what you've been doing with lines, as opposed to this one, which is lines and planes. The big thing here is making use of the dot product between the normal and the direction vector to be able to make a prediction about the number of solutions.